Well, good morning, everybody, and welcome to episode 46 of MakerBot Chats. Sorry, just finishing setting up myself here. But yeah, welcome. My name is Felipe. Welcome to Chats, episode 46. Flexible. It should be a good one as always. And as you know, Alejandra on the back end collecting all of your guys' questions. If you have any questions, you can post them in the comment section to the right-hand side if you're watching this live. Otherwise, the bottom of the page, that also works. But yeah, we have a pretty good one. It's essentially a walkthrough on how to print flexible parts. I have a few examples for you guys here. As you can see, I printed some of them during this week. And I'll be talking about what this material is. Well, maybe if you're interested in the colors that it comes with or on, that'll be also part of it. What are some of the things that you should expect with it, how to print it, and what are some of the challenges that I've encountered while printing with this flexible material. I think it's especially interesting because in a way it opens a lot more options for you to actually prototype with, right? It's a whole additional set of features that you can use with a prototype when you are actually creating flexible parts that will probably connect to a solid piece. Some of the applications can range from either spacers, suckers. I printed a few of the demo cases here that I modeled out. Even if you're looking into like more rubberized simulations, like with these tires that I printed out as well. Just in general, flexible components with piping and fittings that might need a little bit of give between the parts, and as I said, like mainly connection pieces. There's a lot of possibilities here. It does come with a few restrictions, I think, but let's get started just generally speaking about what this material is and how to print with it. So first, to begin, I'm going to take you through the MakerBot page and show you where the material is located at. This material is named SEBS 95A. The 95 comes from the durometer. The durometer essentially describes the rigidity of the material, right? How stiff is it going to be? So 95 means it's fairly flexible. And again, this with 3D printing, as we know, things will change quite a bit depending on the profiles and the settings that you use, right? The material is like 95% stiff. That should mean fairly stiff, but depending on the orientation of the part, the thickness of the part, and especially and critically the infill of the part, the performance will change. But in any case, let's start with just the description of it. It's a labs material. That means you'll be able to print it on both the Method and the Method X using the labs extruder, right? As you can see here in the bottom of the page, it describes what labs is. You can learn more about that as well. But it all comes down to using the labs extruder. What is the labs extruder, you may ask? And I'll show you just now, because I have a few of them here. And I'm actually live printing, and I'll show you what that looks like in a second. But the labs extruder, it's our experimental extruder for the Method platform. What that allows you to do is to print with any third-party material that you might want to. We have a selection of those available on our site that are not MakerBot materials, but we have actually created print profiles and we've tested them enough to know that they will work with the labs and the platform, right? So the labs platform is opened up by accessing, well, with the labs extruder. This is the extruder. It's very similar to our, standard extruder, like the 1XA here. The 1XA is our extruder for example, ABS, ABSR, ASA, and so on. But you can see how the tip itself is exposed. So that allows you, if I bring in my macro lens just for a second while we're talking about extruder, but the exposed tip, here we go, actually allows you to more easily swap the nozzle here, right? And we've talked about the nozzle changing in the past. I won't get into much detail about it. As you can see, this is a little bit burned because I've been using nylon carbon fiber or actually composite materials with this particular extruder. But that's all there is, right? It's the labs extruder that you pair up with your Method printer. Let me remove the macro lens here before it gets too blurry. So the labs extruder, which pairs with the printer here, and then allows you to print with any one of those materials, right? I actually printed an extruder holder for myself. I'll show you guys in a second when I run through the setup. But in any case, that's all that you need to access, all of these third-party materials, and specifically talking about SEBS, it'll be compatible, as I said before, with both the Method and the Method X. You'll be using the Labs Extruder. As a support material, you can use PBA. I'll say PBA and SEBS bind well enough, right? But it's not, I don't have enough experience, maybe that might be the right disclaimer there, on printing with support material and SEBS. I just like it a lot on its own. I need to be printing a little bit more with the support material. And if you click here on, I just clicked here, download the print profiles, that'll open you a free PDF that you can actually browse through and find the different settings that you will need to use when printing with different materials available for labs, and specifically with the SEBS 95A. So that means the actual setup for the slicer that you'll need to use in order to print successfully, right? So it's saying that you should use as a default the PETG material that supports PVA, change the extruder 1 temperature to 260 degrees Celsius, and change a few other inputs here in the temperature for the raft and the speed for the raft. Other than that, you might want to use adhesive on the tape. I haven't, I don't see the need for it, and I printed some rather big parts with it, and it's printing just fine. The material adheres nicely to the build plate, right? It peels off on the corners maybe, but I think that what really helps is the fact that when printing with, and I'll just log in to my CloudPrint account here, but when printing with Method, since the chamber itself is heated, right? As we know, it's a heated chamber. That in its own right, sorry, the password is not working. But that on its own is enough to, let me see. Well, I'll get back to that in a second. But that on its own is enough to make the material adhere nicely to the build plate. And the biggest actual issue here with SEBS is not the addition to the build plate, but rather the overhangs. It's definitely challenging to print with overhangs and SEBS. That's where the support material might come in handy. But yeah, that's all there is to it. You get the material, SEBS 95, really nice material. It's similar to a TPU. Some of you might be familiar with TPUs, but much more stable, right? I've had a way better experience with SEBS than with TPU. It's essentially, the performance-wise, it's similar, on the filament itself, but SEBS, it's just way easier to print. I'm not sure what it comes down to, but it's definitely really, really easy to print. So let's get back into some of the applications, or actually, let me take you guys first through the setup process on the printer here, right? I'll move the camera just a second here. There we go. And as you can see, I am printing right now. There's a lot of reflections. I apologize for that. It's just that the chamber itself is highly reflected, and I have a few lights here. I'm printing just a sphere, right? The sphere has a rather narrow contact point with the build plate, and you can see that it's printing okay, like for the top layers. The bottommost layers, that's not an addition issue. That's because of the way that SEBS cools down, right? It doesn't really like to have a lot of overhangs, especially unsupported overhangs, which is what I'm printing with right now. I think the print will still succeed, but you have to be mindful of that. As you get away from the build plate and you have any of these, particular type of overhangs, you might see some issues, right? But all there is on the printer is I've side-loaded the SEBS spool right on my Method. I'm running, of course, as I mentioned before, the Labs extruder in there. You can see the exposed tip right there on the left-hand side, right? That's my main material extruder that's being exposed. And that's all there is, right? I have, as I said, like a better setup now on the printer where I actually place my Labs extruders here in a holster to the side. I think that this is really handy. If you guys would like access to that STL, I can definitely share it with you, but it's essentially bracket that hangs from the side of my Method and allows me to place the extruders neatly there. Now, going down to the parts and talking about the actual applications on this material. I have a few of them, and I'm hoping that that sphere will finish printing right on time before we are wrapping up. But I'll take you through some of the simple parts and some of the more complex parts, right? I started with something very basic. I think that one of the most common examples of flexible printing is actually like phone cases. You'll see a lot of those out there as STL files in Thingiverse and whatnot. And you can see that this is a rather big case. This is 6.1 inches across, and it printed really well, right? It actually printed laying flat. Let me move stuff around a little bit, but laying flat against the build plate like that. There's really no delamination happening here on the first couple of layers, and the part itself is impressively flexible, right? And it goes back to the original shape immediately. So, really nice first proof of concept, rather successful. It's also a very straightforward piece, right? If anything, you have a little bit of an overhang here with these corners that are essentially meant to clip onto the phone's edge, right? Just to get it in place. But yeah, really flexible. And as I was saying before, naturally the flexibility will change depending on the actual shape of your part. In this case, the back side of the case, you'll see, maybe I'll try to make it happen here, right? It's really flexible just because of the way that the layers are oriented there. But here in the corners, because of that, extra radius and the shape of that particular section, the part it's going to be much stiffer, right? It's going to be fairly hard, if not impossible, for me to bend this corner out. And again, that's not due to any change in the material itself, but rather in the inherent geometrical properties of the material, right? Of the shape. As the material stacks up in a corner, and you might have seen this with just folding paper, it's going to have a different structure and different stiffness than the rest of the part. So bending the part here we go, to the side maybe, it's going to be way more flexible than trying to bend it on the corners, just because of the way that the material stacks up. But even then, one of the things that I really like about this particular material SEBS is that if you guys have had any experience with TPUs, it's common for it to delaminate fairly easily when you're flexing it over, right? It's hard for those layers to actually stick together as a single unit. And I think that this is actually just greatly in part thanks to the heated chamber again. That creates enough thermal stability for the layers to better bond and essentially allow for less delamination on the parts. I'll bring it closer to the camera, but it's like I can bend it quite a bit, and the layers are not delaminating, right? You can see how clean the part is still there. How clean the wall is, even after all of that bending and creasing and whatnot. So I started with this particular part, then I moved on to a little bit more, a more complex one, which is this case that included the opening for the camera. However, in this particular example, instead of printing it laying flat, since I had this feature, protruding for the camera, it's actually out of Pixel 6, I printed the part vertical, so standing up. I was a little bit afraid that maybe the part would start wiggling around as I printed up and as I got further away from the printer. But I'm happy to report that actually the sturdiness of the method delivered in that regard as well, because the part really didn't wobble that much. You can see a little bit of these creases happening here, but that's actually because of the way that, again, the thermal changes in the material, right? So there's a little bit of warping happening there. It's only noticeable against the light, right? You can see how there's a little bit of a crease here and here, like two creases. But all in all, the part printed successfully, right? And I still have the same, and again, by the way, all of this was printed without supports, which is also rather impressive. This bridge is about 2 inches, and it still was able to bridge it out, I would say pretty okay. Definitely would be worth testing it out with PVA supports, just to see how that improves the printability of the part. and maybe changing the orientation. So laying it flat, allowing for the PVA to create that layer at the beginning of the part, and then testing out that result. But all in all, just started it with without supports. I wanted to print something quickly and test out the idea for you guys. Then here I have just a flexible pipe, another good example for this material, and another sort of interesting way of thinking about it and how the material will change depending on your geometry, right? So in this case, the wall thickness that I've got here is 3 millimeters, and the part is already it's flexible, but it's rather stiff, right? It's not, it's not buckling super easily. I still can make it bend quite a bit. And again, for me, the biggest takeaway here is how stable the layer attachment is, right? How stable those layers are, even when I'm applying consistent and repeated forces to it, the part still behaves really nicely. So I don't know. For me, it's a rather interesting and promising example, and also important to note and this brings me to my third example. The infill that you use on the parts is also going to affect quite a bit how the part behaves, when you induce any stress to it. In this case, I printed out these two tires, right? This one has 20% infill, and this one has 0% infill, and you can see how, applying the same force to them, right? Like just a light force on the left one, a light force on the right one. The left one is already buckling, and the right one is not. I still can feel that there's some, it will give if I press hard enough, but definitely something to consider. The fact that the infill in your parts, the number of walls in your parts will definitely affect the performance of the part and the amount of flex that you get, right? If you wanted to have something more flexible, think about reducing the amount of walls or reducing the infill on the part, right? So this is 20%, and the part it has some give, but it's fairly stiff as well. Final example before I jump into the Q&A section is these rubber soles that I printed also overnight with the same material, right? This structure is called the Voronoi structure. It's essentially simulating cells, sort of like bubbles, collecting in a single area. It's a rather appealing shape on its own, right? But it becomes even more interesting when you actually press up against it, because it allows for quite a nice bend, right? And in this case, the structure might not be ideally oriented just because it has a lot of give, in this direction, not so much on the z-axis, which would be kind of like where my feet or my foot would be resting on, right? But the idea stands, is how do I create something that's flexible, that will have some give, and again, the orientation of the geometry, not the material, but the geometry will definitely change the direction on which this particular shape will flex. It has a lot of flex on the XY axis, so this part was printed flat on its back against the build plate, but it's definitely stiff on the Z axis, right? I'm not going to have it buckle in this direction. However, this part, it's similar in that I'm using the same Voronoi grid on, the heel of the shoe, but I printed it out at 5% infill, and instead of printing a grid that would be sort of self-supporting, this new shell is now almost hollow inside, and that allows me to actually have a nice cushion here, right? If I was prototyping a running shoe, if I was prototyping just an insole, it would be really, really, really good at simulating different densities of the material, right? So as I said before, this is 5% infill, and look how much give it has. And again, the same idea of being able to flex it quite a bit and not delaminating the structure, which is, I think, one of the issues with other TPUs and other printing systems that I've used in the past, where delamination actually becomes kind of a real pain when using this material, right? So yeah, with that, I'm going to start jumping into the questions just so that I give you guys enough time to ask them out. And this sort of covers it all. The part is still being finished up. While it does, I'll just run through some of these Q&As that we have, that you guys actually have kindly submitted. Let's start with what are some of the applications where this filament is used? Well, as I was saying, you can think about it as, you know, simulating different urometers, different materials, like you know, when prototyping shoes, when prototyping you know, rubber parts, like in the case of the toy industry, or even when creating connections, like flexible connections and piping for, I wouldn't necessarily use it for liquid purposes, but maybe to manage some gases. Like if you have an extractor and the fumes are not that hot, you can definitely run it or create the attachment pieces with SEBS. What are the advantages of working with SEBS? Well, mainly it comes down to that flexibility, right? So being able to print flexible parts, I think it's super useful. And it just adds a new dimension to your prototypes, because they no longer need to just be rigid and stiff. They can actually be well, flexible, and in that regard simulate different rubbers or different properties of the parts themselves. What is the optimal printing temperature? And as I was showing you guys before, again, going back to, let me take you guys back to the website and the profiles. The extruder temperature is going to be 260 degrees Celsius. And it just changes a little bit for the raft base. I have not been printing with a raft. I think that you really can get away with it. I mean, all of these parts that you see here on my camera were printed without any raft at all. So yeah, and you might want to throttle down the speed for the raft as well, just to make sure that it really adheres. But I haven't had the need to use a raft so far. Let's see. Back to the questions. Does this filament absorb moisture? That's a good one. I don't think it does. It's definitely not impermeable, right? It all depends on the application. But regarding like storage for the filament, you can definitely keep it, you know, you don't have to be so careful with it as you would with a PVA, any one of the soluble materials. I keep my SEBS just, you know, outside of any mylar bag or without any desiccant, and it prints just fine. So the filament on itself, it's not as sensitive to humidity, you know, by any means. My material started to short feed or bind up in the extruder. What can I do? Okay, it depends on the type of extruder that you're using. So somebody's saying that the material actually crumbled up inside of the extruder. If you're using some of our older generation experimental extruder, like the one that was used for the Replicator Plus, you could open up that extruder and make sure that it's not, you know, spooled up in the encoder wheel. That's usually one of the issues, because the material will just wrap around the encoder wheel and stop flowing through. If you have a lapse extruder, you won't be able to open it up like that, but you can definitely remove the nozzle, see that it's not stuck in there, and I would also recommend running a cycle of loading and unloading in the method, so that it actually, you know, starts to flow better. But yeah, that would be the takeaway. Essentially, you need to open the extruder as much as possible so that it's not caught up in the encoder wheel. It shouldn't be the case for the lapse in the method. If you have the older lapse extruder for the Rep Plus, that might solve it. So just opening it up and releasing it from the encoder wheel. What support material should I use when printing with SEBS? The default is PVA, right? I don't, yeah, after printing with rapid reads, and we've talked about, if you guys joined us in the past week or so, after introducing rapid reads and seeing how easy it is to print with it, I really miss that we don't have it available for other materials. But the short answer is you should print with PVA. I don't have enough experience with that mix just yet. Most of these parts have printed without any supports at all. How's the bed addition for this filament? Is it glue or extra addition necessary? No, actually, you know, the documentation says that you might want to use, let me go back to the documentation here, that you might want to use, you know, tape for larger prints. I was showing you guys before this particular example, right? It printed out with any adhesive on the build plate. I think that the big difference here is that with the method, that slight increase in the printing chamber temperature is enough to just basically allow for the material to nicely adhere to the build plate. If you see some issues, do add the tape. I haven't had the need for it, and again, these parts are fairly big, so this is 6.1 across, it's about 5.4 here on the main axis, and it printed out with any major issues, right? It depends on the part. So far, I haven't had the need to print with adhesive or tape on the build tape. And I think we might have one last question. Give me 1 second. Nope, I think that's pretty much it. So again, thank you guys so much for joining us today. It's always a pleasure to talk to you. And again, really exciting material. I think that we can definitely do some more experiments in the future with it. It's a first pass at it. The supports question, I think it's a good one. Like just doing more supported parts to see how they perform. All in all, I try to skip supports whenever possible just because it improves print speed. And I don't have the added step on dissolving the supports, especially with PVA. When I'm printing with rapid rinse, that's a whole completely different story because rapid rinse, it's incredibly easy to dissolve. If you haven't heard about rapid rinse, you should definitely check it out in our site. But yeah, with that, thank you guys again so much for joining us today. If you have any questions, you can reach out at hello@MakerBot, Felipe@MakerBot, or in our social channels, both Instagram and Twitter, @MakerBot, with any questions regarding flexible parts or just MakerBot in general. So thank you once again, and happy printing. Bye.